proposing is pretty straightforward. It's the following one. Just like when you're driving your own car, how do you drive your car? When you drive your car, you look out for a quite long distance, right? And you calculate something in your brain, you pass that information, decision, and you press the pedal, right? When you press the pedal, the car moves on, you have new information coming in, right? Oh, there's somebody, some U-turn or something. The new information comes in, you reprocess what you see, and you reprice the pedal. So in a nutshell, what you do is that you take a longer view of the available information and you make a decision that is best for this longer period of time, and then you process it just for the next time step, And then you move on, you have new information updated, and you compute it again, but you only press the pedal for the next time period, and you move on. Right? So that's the idea. So instead of just looking at the next 10 feet, right? Because if you just look at the 10 feet, you might, speeding up, not realizing, 100 feet down the road there is a, big accident, right? So the idea is that to try to leverage the most recent, most accurate information and trying to do more extensive computations so that you have an overall better portfolio of schedule. And the same principle can be applied to you and me, to the demand side as well, because on demand is also certain flexibility. So we're not going to talk about the detail. And this is how you implement it in the marketplace. In the marketplace, when you want to do it in a centralized way, that is, that is the sort of the best way to do it, but it's going to be very costly computationally because think about ERCOT or Texas Power Grid operator trying to run a monstrous super optimization problem by including every single wind turbine's behavior and every single wind turbine's forecast. And that's doable, but it's very computationally costly. Instead, what we are proposing is that every single one of us can make this best decision based on our own forecast of how much wind is blowing and how much solar is available. And making that decision then submit back to the system operator are very static sort of supply curves, right? So for those of you who have taken the Econ 101, the supply curve is how much you are willing to sell at which price, right? But that supply curve already internalizes some of the technical constraints, right? Some of the technical constraints. So that's getting into the technical part. And that is how you bid. And one thing I want to make sure to convey to you is that, you think about the other side of the equation, which is a completely different problem, but it's actually mathematically the same. That is the problem of managing the demand, right? Think about this room. Do you care if this room temperature is 72.02? As long as this room is between 70 and 75, I'm okay, right? So what is driving the the temperature deviations? What is driving the ups and downs of temperature? It is underlying thermodynamics, right? So, but in a nutshell, temperature will not go from 0 to 100 instantaneously. There is certain thermal inertia there, right? You have to go some smooth way, right? And that smooth way gives you a little bit of a headroom to flexibly decide how much air conditioning you want to charge now or how much you want to charge for the next 10 minutes. Because now, having this information from the prices, you know on the grid level how much is needed for consumption. And that can be reflected from the price, the relative high, the relative expensiveness of price. And as a home manager, what you can do is that you can maintain the comfortness zone, while trying to minimize the total payment you have to pay for the electricity, assuming if there is a real-time price. Right? The same, so that kind of a idea is the same as on the generator side, how you do this so-called look-ahead dispatch. Right? That is, you look ahead, you look at the expected price, you look at the expected evolution of the temperature dynamics, and you make sure that on one hand, your comfort zone is met. On the other hand, you allow this flexibility of allowing the air conditioning to do when to charge and when to discharge. Because maybe the next 10 minutes, the price may be much lower. So you may just want to turn off the AC for this 10-minute interval and go for the next 10-minute interval, and just allow the temperature to go up a little bit while still not violating your comfort zone, right? So for those of you who are interested, our students have already developed an Android phone application for doing that. It's called Grid Smart. You can actually go and play with that. Talk to James Carroll. He's the main developer behind that. And also, this can, for those of you who are interested in environment and policy, this kind of a framework can also be expanded to policy-dependent look-ahead dispatch. That is, depending on how much, what kind of emission policy you might have. Who knows, when this is going to happen? But in case this happens, this dispatch framework will be able to actually also incorporate environmental concerns, be it carbon tax or carbon cap and trade or carbon quota. All this can be done. I just want to show you one picture. With the same hardware, that is, in the same system, the same generation portfolio, depending on the way you schedule the system, right? Depending on how much backup unit you are doing, depending on how you leverage this near-term forecast information. Same hardware, no change of hardware at all, but just changing the way you operate the system, you don't see any comfort zone, you don't see any degradation of your comfortness. In the meantime, you saved about 37% of the dollar cost and about 18% of the emission cost, right? And to me, that is really the low-hanging fruit, where potential gain could be and should be leveraged, right? So this is what we have proposed for this distributed look-ahead dispatch framework. We're also very glad to show you some very exciting recent extension working with Gary and Xinxing and Professor Jensen in the statistics department. That is the so-called spatial temporal forecast. Right? The idea is also very interesting. One thing that one might ask is, okay, I know wind is very volatile, but if you aggregate the entire US wind generation, right, would that be somehow more smooth because of the sort of law of large numbers? I mean, that's a natural question, right? What do you think? Yes or no?
It's like balancing a stock portfolio almost. Some idea.
Yes. Quite to our surprise, it's not that much of improvement. Look at the red curve and look at the other curves. The red curve is the total California wind generation, and these 5 other colors represent the 5 largest wind farms in California, spatially across more than 1,000 of miles. So presumably they should be pretty good sample spaces, right? Because they are far away, they are somehow maybe uncorrelated. Unfortunately, let me ask you, is this one very smoothed out? I mean, that's the fact, okay? I'm not making this up, this is the fact.
They all are on the same coast though, would that affect it?
Right. So the punchline is, even over a very large geographical area, the wind farm still tend to be very spatially correlated. So that violates the assumption of law of large numbers, right? Because you have to have independent distribution in order to have things smooth out, right? So the question is, okay, these things are very spatially correlated. So really, we are doomed. I mean, what can we do? We collect all the wind power and it's still very volatile. What do? Well, people will say, okay, why don't you couple with solar? That might help you a little bit, but not much. So, I think our idea is that, okay, yes, they are very spatially correlated, but hey, why don't we just turn the story, upside down? That is, let's turn the bad things into good things. Yes, we know they are not quite smoothed out, but hey, the spatial correlation tells us that maybe you can leverage this spatial correlation and do something good for better forecast, right? Very simple example. You can let the upstream wind talk to the downstream wind. And because of the sensors and communications, they're all in play, right? You can allow the downstream wind make a much better forecast result if you allow them to know what's going on in the upstream, right? Very simple idea. Actually, it turns out to be quite useful. So this is an example of Columbia River Gorge between Oregon and Washington. There's 3 wind farms. Now the wind sometimes blow this way, sometimes blow that way, and then we allow the communication to be dynamically adjustable, so that they always get to know what's going on in the upstream, right? And that actually can help you a lot in terms of better forecast. So we're not going to tell you too much about detail about it, but hopefully we can report you much more detail a few months later. So these are just some of our activities going on. I think what we're trying to do is that we're trying to use the systems approach with domain-specific knowledge and try to understand what is the role of information for future electric energy systems. And back to the original question, I think smart grid maybe need not only the hardware to be smart, not only need better IT infrastructure and power infrastructure, but really need to have a better understanding and interaction between the information and the physical of our future grids. These are some references. You can find me by email me or just talk to me in my office. Thank you. Yes, please.
You talked about the variability of the wind and such, and that I can understand it's going to be a problem if you want to produce a lot of electricity or a large percentage of your electricity via solar.